Okay, so in the last week, I guess as I have already announced at the very first week of this lecture, uh, uh, in the upcoming semester, hopefully the COVID-19 has completely removed out on Earth. Anyhow, uh, in the in my lecture to be offered in the upcoming fall semester, I'm going to keep going on PN junction theory and MOSFET transistor. So if you're interested in understanding the device physics of MOSFET as well as the rest part of the PN junction theory, please register my class and we're gonna meet again, hopefully in offline classroom, and we're gonna study more. Anyhow, for the limited time, I will do my best to deliver my knowledge to you. Uh, and hopefully, I'm going to cover up chapter 5 and 6 because I'm planning to record uh, some more overtime, some, sorry about that, I got a sore throat, some more video running time. All right, so let's start. In chapter 5, uh, the textbook said, uh, as the very first step to analyze the PN junction contact, uh, let's begin to understand and figure out the physics, how the charged particles are distributed out across the PN junction. So in that sense, we should do the analysis for PN junction electrostatics. So as I have told you in when we have learned MS contact, the electrostatics indicates we should have understanding how those four major parameters such as charge density, electric field, potential or voltage, and the electron's energy in the MS contact are closely associated to each other. So those four main major parameters are associated to each other. So we have learned, Gauss's law, Poisson's equation, and the definition of electric field intensity, and electron's energy is defined as minus q times potential. So using those three equations, we can have some deep understanding how those four main parameters, charge density, electric field, potential, energy, are closely associated to each other. So we're gonna repeat that process again, but with PN junction. Okay, so let's do that. So in the last movie clip, I have told you that. Let me change. Okay. So in the last movie clip, we have learned. I have announced that the the one thing that we didn't study to understand a PN junction in integrated circuit chip is this PN junction part. Well, actually, the metallic material would be bonded or deposited onto the P-type and N-type. But since the P-type region comes from the substrate, wafer substrate, right? Therefore, we need to make a ohmic contact. Therefore, P++ heavily doped P-type silicon material is necessary uh, to build up the ohmic contact between metal pillar type contact and heavily doped semiconductor region in the P-type silicon substrate. And of course, definitely we need M++ heavily doped region to build up the ohmic contact between metal and N-type semiconductor. So in that sense, we need a very heavily doped semiconducting region. Now, in the last few movie clips, we have learned how electrons are moved back and forth between matter and P++ or M and M++. However, we didn't study the details how electrons and holes are moving across the Pn junction. So from now on, let's remove those parts because we have learned it. So let's keep an eye on Pn junction only. So herein, you're gonna see that P and N. So usually N side is grounded or referenced so that the voltage difference across Pn junction diode is denoted as V sub A, applied voltage, and that is positive, and there's negative, usually 0 volt. Then the voltage difference between P and N regions are indicated as V sub A, and positive current direction is defined as the current flow from P to N. Okay. All right. With that in mind, let's do the qualitative electrostatics analysis. So the first main parameters when analyzing electrostatics in PN junction diode must be the charge density across PN diode. So herein, just intuitively, you may expect that P-type material, its a majority carrier is hole. So P-type material has a tremendous amount of holes. However, in the N side, the number of hole is very small compared against the total number of electrons in N side. So diffusion force should be applied in this situation. So many holes would prefer to be diffused toward the N side. Similarly, many electrons in N side would be preferred to be diffused into the P side. Therefore, near the physical contact area, some interaction would be happened. So what kind of things, what kind of events, physical events would be occurred near or at the interface of PN junction diode? So for that purpose, let's use the depletion approximation again. What was the depletion approximation in MS diode? You remember, right? Yes. At a certain region, suppose that the physical contact area, contact region is denoted as x of 0, and along the x direction, I guess at x is x of n, because this is inside the region. So when x is x of n, the depletion is abruptly stopped. In other words, in this region, all the electrons are diffused toward the p side, so no electrons in this region. That means this region is fully depleted of electrons. However, in this region, the N-type semiconductor material is well neutralized with electrons and ionized acceptors, which is positively, negatively accept, donors. Yeah, sorry about that. Again, in this region, the electrons in N-side material has been well neutralized with positively ionized donors atoms. Okay, donor atoms. So that is the reason why N is equal to Nd, and that is Nd plus, because we have assumed that the fully ionization. So we're gonna keep an eye on in this region, depletion region. Okay, so here, if I draw the charge density plot, which means a charge density on the y-axis, and x-axis indicates the physical displacement across PN junction diode. So the unit is coulomb per square centimeter. X is centimeter. So at x of xn, beyond xn, all the electrons in n side is well neutralized with the positively charged donors. Therefore, charge density is 0. Now, you remember this equation. Charge density rho can be written as Q unit charge times P minus N plus Nd minus Na. But in N side, P is negligible, acceptor is negligible, so that minus N plus Nd. However, in this region, the number of electrons are determined by donor's atom. So N is equal to N. So plug in here Nd, then minus N plus Nd. Therefore, rho is 0. Physically speaking, all the free electrons coming from the donor's atom are well electrostatically balanced with positively charged donors. So in terms of charge density, 0 at x of in this region. Okay. So same physics would be applied onto the bulk region of P side. So all the holes are well balanced with ionized, negatively ionized acceptors. So the charge density is Q times P minus N plus Nd minus Na. But in P-type bulk region, the number of electrons is negligible compared against the number of holes. And here donor is nothing, right? Acceptor is more injected. So P minus Na. But you know, the number of the hole is equal to acceptor's concentration. So if you plug in the Na into the P, then rho value is Q times 0, 0. Okay, so well neutralized region if X is smaller than minus XP, because I have defined that the origin point across X direction has been formed and defined at the physical contact between P and N. Okay, now the next job that we should tackle out is this. How much charge density we can expect in between 0 and xn. So since we are using the depletion approximation, the depletion events are over at x of xn. So below xn, all the electrons or all of the regions are fully depleted of electrons. However, beyond xn, all the electrons are well neutralized with donors. Okay, then what is this value? Yes, you're right. Q times N sub D. If there is no specific, conditions how the dopant atoms are distributed out in the N side, the basic assumption is that donors are uniformly distributed out in the N side material. Therefore, the doping profile of N-type material is uniform. So we can simply claim that Q times N sub D is the charge density. Why is that? Again, go back to the generalized equation for charge density, Q P minus N plus Nd minus Na. In this depleted area, no holes, no acceptors. Now we are in N side, but many donors, but here no electrons. I said this is depletion region. So this region is depleted of electrons, so N is 0. All the electrons, free electrons in N side in these regions has diffused toward the P side. So nothing left, no electrons left behind in the region of 0 and Xn. Okay, so the charge density is Q times ND. So this level y-axis, y-intercept is Q times N sub D. So depending on the doping concentration, the charge density in the depletion region can be determined. So similarly, the depletion region on the P side can be understood simply. So what is this value? Yes, only ionized acceptors are left behind because all the holes are diffused toward the N side. Okay, so here the charge density value is Q times, P minus N minus Na, but no holes, all the holes are depleted out, and no electrons. This is P side, not too many electrons left behind, and donors, no, P side, right? So acceptor is dominant one. So compare against the Na, and D is nothing, so you can ignore it. Then this value is Q times minus Na. Okay, so now the charge density value is below zero, so this value is minus Q times Na. Right, almost done. So let me erase my notes and let me clarify the y-axis, y-intercept. So here Q times ND, here minus Q times Na, and this Xn plus Xn, and that is minus Xp. So in this depletion region, the charge density are well separated, plus charged area has been formed on the N side, and minus negatively charged area has been well set up on the P side. Okay, so why this charge density plot rho versus X has been drawn? So the basic assumption is we have used the depletion approximation so that all the electrons in N side has been diffused toward that P side, and all the holes in between 0 to minus XP has been completely diffused toward the N side. So there is no holes available in this depletion region. However, the donors and acceptors are, tightly bonded with the four neighboring silicon atoms, as we have learned in the very first half of the lecture. So this Na and Nd are definitely immobile, but they are ionized so that here plus charged area and minus charged area are popped up and formed. Okay, all right. So the very first step in doing the analysis for electrostatics for PN junction contact has been done. So the next job is to look for the electric field intensity across X, across PN junction diode. So as we have done in MS diode, let's repeat that work again. So please remember what we have done from step number 1 to step number 2 for MS contact. Yes, Gauss's law. So Gauss's law can be mathematically expressed with a Poisson's equation. So let's write down the Poisson's equation here. So the electric field intensity can be varied with respect to X, and this electric field intensity, the first order derivative of electric field intensity is proportional to the charge density, and proportionality constant or coefficient is 1 over dielectric constant. Okay, all right, so using this Poisson's equation, we can solve electric field intensity as a function of X. Why is that? The charge density as a function of X is this, plus Q and D when X is in between 0 and Xn, and rho X is minus Q and A when, say, if X is in between minus XP and 0, and otherwise 0. So we can separately solve Poisson's equation for 3 different reasons. Okay, so let's do that. So dE dx is equal to epsilon silicon, and let's solve this first. Plug in Q times ND. Then what is electric field intensity? After taking first order derivative, we're gonna get this. So the original, analytical equation must have this form: Q and D silicon X plus certain value, say C1. Okay, so it seems that this part, straight line, right? First order, analytic equation. So now we should know the value of constant C sub 1. So how to get it? Yes, when if X is Xn, the electric field intensity must be 0, this point. Okay, because beyond Xn, so no charge. So no charge means here 0. That electric field intensity must be constant. But uh, at x slightly, this area, x and minus alpha, in this area the electric field intensity is negative. So because of this positive and negative charge region, so intuitively you may guess that the electric field is formed from plus to minus direction. So since this direction indicates positive value, so this electric field from plus to minus region, this value must be negative. So, at this region, the electric field is non-zero but negative. So in the end, at this point, beyond the axis of Xn, the charge density is 0, so electric field must be 0. So definitely you may guess that at this boundary x of Xn, the electric field intensity must be 0. So plug in x of Xn here and 0 here. Then C1 is equal to minus QND over epsilon silicon Xn. Then plug in this value back to the original equation. Then the EX is equal to QND epsilon silicon X minus Xn. So this is the analytical equation for electric field intensity, where from 0 to Xn. And if you draw E versus X plot in this region from 0 to Xn, you're gonna get straight line. This is Y is AX plus B. So following the form of the Y is AX plus B, you're gonna expect that the straight line. And here the question is, what is the slope? Yes, Q times ND divided by epsilon silicon. So depending on the doping concentration in N side, if you increase the doping concentration of N side in Pn diode, or if you decrease the doping concentration in N side of Pn diode, the slope of electric field intensity as a function of X would be modified. Okay. All right. So let me raise my note again. And no, let me change my pen color. All right, let's solve this part one more time. So I'm talking about this reason, minus xp to 0. Okay, so the charge density has been denoted as minus q times Na. Okay, and then just into the Poisson's equation, dE dx is equal to charge density q minus q times Na divided by epsilon silicon. So electric field intensity must be minus q Na epsilon silicon X plus some constant value. Then we should come up with the boundary condition for this equation. So boundary condition is here. When x is minus xp, the electric field intensity must be 0. So plug in here minus xp and here minus xp, then the whole value must be 0. Okay, then C2 is equal to, this is minus, so if you move it to the left hand side, plus Q and A silicon and minus XP. Okay, then now plug in the C2 value back to the original equation, then you're gonna get this. X plus XP. Okay, then if you draw this equation in the E versus X plot, you're gonna get this straight line. Okay, then the question is a slope. This slope is the function of Q times Na divided by epsilon silicon. So depending on the doping concentration on the N side, P side, the slope in E versus X plot should be determined. Okay, so for given Pn junction diode, the acceptor's concentration and donor's concentration, those two are the key parameters how the electric field intensity would be modified along the x direction. Okay, all right, so we're almost done for step 2 and step 1. So the left thing is step 3 and 4. So let me erase my note and change my color to red one. Okay, so now as we have learned which equation would be useful to connect those two different concepts, field, electric field, and potential. Yes, dV dx is equal to minus electric field, as we have learned. So in the step number 2, we have the whole equation for each reason, right? And I didn't write down all the details because I have removed it, but you must have taken your own notes. So plug in, write down the equation here. So for those two different regions, you may solve this first order differential equation. Okay, so plug in E of x here and take integration for both sides, then you're gonna get v of x is blah 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 blah. So to solve this first order differentiation, you should know and you should have one more boundary condition. So what is it? Since this is a potential, so one chance is you can define the reference voltage at any place. At any value of x, you can define this x value, say at x of minus xp, the potential value is 0. So this is the reference point. Okay, so the author of the textbook has defined that the reference voltage, in other words 0 volt, has been defined at x of minus xp here. So when you solve this first order differential equation, you need one boundary condition. That is when v x is minus xp, then the potential value is 0. So using this boundary condition, you can completely solve and get this solution of this first order differentiation. So please do that by yourself. I hope you to solve this first order differentiation by yourself. If not, please ask a TA or me, or drop by my online office hour. Or in your textbook, very detailed step-by-step solutions are provided. Okay. All right. So we have done for the electrostatic potential for the P side. What about the N side? Yeah, you can repeat all the processes again. How to do that? You can just plug in the E of X value into this integration, and you can solve this first order differentiation. However, you need one more boundary condition. What is it? In the range between 0 and xn here. Previously, we used this boundary condition, but in the N side, what kind of boundary conditions are necessary? Yes, at x of xn, how much voltage difference has been formed? So we have no idea how much voltage difference has been occurred across Pn junction. So, however, the one thing that we know is that there is potential barrier height. Why is that? Why there should exist a potential barrier height between P and N? Why is that? Let me write down two dishes. So this dish contains water. So water is corresponding to electrons. So we have a p-type dish and n-type dish. N has abundant of electrons, so it must have tons of water in itself. So more water has been included in n-type dish, but in p-type dish, not too much water has been contained. So now the job that we are going to do is to make a physical contact between P and N dishes. So let's combine them physically. And then since P and N are combined together, so this interface area should be removed. Then what would be happened for water here and there? Yes, many electrons or water droplets would be fallen into the p-type dishes. So in the end, no, let me write down here together. So the final, uh, final shape of P plus N dish is this, and the waters are evenly well balanced out across the Pn diode. Okay. Then question is, originally there is this difference, but now no difference because the water in N side has been spilled over into the P-type dish. What would be left behind? Yes, this energy barrier height has been removed. In other words, originally there is a potential barrier height between P and N. Okay, so that value, we have no idea how much is it, but across Pn diode there is built-in potential. So I said built-in. Built-in means spontaneously, in nature, not from external force. Okay, so spontaneously P and N-type materials has formed the built-in potential. So we can use this value as a boundary condition when solving the first order differentiation here. Once you plug in this E of X here, then you should want more boundary condition that is defined as this. Okay, but still we have no idea what it is, just a constant value. Okay, All right. So now we have solved electrostatic potential. Then the last job in qualitative electrostatic analysis is this band diagram. So from step number 3 to 4, the band diagram is this. Electrons energy is defined as minus Q times electrostatic potential. Since you know the electrostatic potential has been drawn like that. So before moving forward, let's take a look at the shape of the electrostatic potential plot. So since from step number 2 to step number 3, the job that we have done is this. dV dx is equal to minus E. So if this electric field is first order equation, then this potential must be second order equation. So second order equation has a two different shape, upside down or downside up, parabolic curve shape. Okay, so part of the parabolic curve shape has been found here. Okay, and part of the parabolic curve shape has been found here. Okay, but what about here and there? Yeah, straight line. Why is that? Because electric field is zero. So if you plug in here 0, then potential value must be constant. Okay, so that is constant, and that is constant as VBI, that is constant as VB0. Anyhow, between or in the depletion region of Pn diode, the electric field intensity has been linearly modified in the P side, and another linear modification can be occurred and observed in the N side. So correspondingly, in the P side and in the N side, the potential values are modified following the second order equation. So herein, when we draw the energy band diagram for PN junction diode, the potential electrostatic potential must be following the second order equation. Okay, so this energy of electron must be drawn and illustrated following the second order equation. So, however, notice that there is minus sign. So everything is upside down. So just for given a certain horizontal line, you can just simply flip over the potential plot like that. Then you're gonna get this straight line, another straight. Let me change color. Straight line, straight line, and that is upside down parabolic. So if you flip it, it should be like that. Okay, so you can find the parabolic curve shape, and beyond and depletion region of P side here, the curve is downward. So if I flip it, you're gonna get this curve shape. Okay, so you can find out that the band diagram is this, looks like that. Okay, and here a straight line. So if I flip it, another straight line, so you're gonna get this. Okay, so the conduction band edge line has been split into 4 different areas, right? So 1, 2, 3, 4. And now you can draw the conduction band edge line for each region. Okay, but definitely the region number 2 and 3 are corresponding to the depletion region of Pn diode. So using this equation, energy of electron is minus Q times potential. Since you know the potential plot, you can draw the energy of electron. But this energy of electron, y-axis in energy band diagram indicates energy of electron. So you're gonna find out the conduction band edge line. So again, here, I'd like to say you that this is straight line. That is another straight line. However, here is corresponding to x of 0. That means a physical interface or physical contact between P and N. And the depletion approximation has been adopted. So at minus xp and at plus xn, depletion layer has been limited in between minus xp and plus xn. And conduction band H follows a second order equation, so parabolic shape. And another, second order equation, so parabolic shape can be used, it should be used when you draw the energy band diagram. So you have some experience. Please draw the energy band diagram across Pn diode. Then many students are doing this. This is wrong. You should watch out. Did you split four, 1, 2, 3, 4, 4 different reasons, and you should draw 4 different segments, and then just to connect 4 different curves together. Then you're gonna get the conduction band edge E sub C for Pn diode. Afterwards, silicon band gap energy is constant, 1.12 electron volt. So just to copy the old curve shape from here, the same curve shape, from here, same curve shape, and the same constant. And that is in the case of balance band edge. Okay. Afterwards, intrinsic Fermi energy level E sub I is following the conduction band and valence band edge profile. Okay. The last thing is a Fermi energy level for Pn diode at thermal equilibrium. So when P-type and N-type are separately exist, P-type material has its own Fermi energy level. N-type material has its own Fermi energy level. So EFP and EFN must be different because it's a different system. But once P and N are combined together, since they are formed as a single system, the Fermi energy level for that single system, in other words, Pn diode, must have a single energy level for Fermi energy level. Therefore, EF is single valued. That means, this EF is very single valued, and it is constant across Pn diode because we didn't apply any external force. So this Pn diode is existing at thermal equilibrium. So the Fermi energy level can be drawn like that. So as we have learned, this EI minus EF value gives us some idea how lightly or how heavily the p-side semiconductor has been doped. You remember if n sub a is 10 to the 15, then this EI minus EF is take a 5 only times 60 milli electron volt, then 0.3 electron volt. So you can directly estimate how much energy difference can be found between EF and EI. What about the inside? Let's say donors concentration 10 to the 16. And then, EF minus EI on the N side is, take a 6 times 60 milli electron volt. Definitely at room temperature, is 3 electron volt. So this energy difference is 0.36 electron volt. Okay, so from this slide, I guess this slide is very significant and important because we are taking advantage of using all the knowledge that we have learned in the first half of the lecture. And of course, we're doing very similar works for MS content, but this works has been done with Pn diode. But the thing uh, that looks very different from MS diodes electrostatic analysis is this, since both sides is semiconductor material. Okay, so banding can be found and observed and drawn on both sides. Okay, so I guess this would be very good question for your final big assignments. So please practice yourself to catch the physics, how the electrostatics across Pn diode has been formed, and please train yourself how to derive all the detailed equations for each physical value. Okay, and definitely you should draw the exact shape of the energy band diagram instead of doing this. Okay, do not this anymore. Just draw clearly and then connect them. So please practice at home as much as possible. Okay. All right. So I guess this would be a good timing to have a short break time. So see you in the next movie clip. So in the next movie clip, I'm going to tell you some more details how to get rho x electric field and potential value. Well, actually, we have done already, but in the next movie clip, I'm going to repeat and review what we have done in the first class. Okay. So please review all the details how to do the electrostatic analysis. Okay, that's it. See you in the next movie clip.